In the last video, we proved that in hyperbolic geometry that the sum of angle measures of a triangle is less than 180 degrees or pi radians. Okay, so this is this is hyperbolic geometry. Now, one immediate consequence of this that is something you're working on in your problem set is that the angle sum of a convex quadrilateral is less than 360 or 2 pi. Okay. Now, I'm not going to go through and prove that, but just as a quick reminder, a convex quadrilateral means that any segment joining 2 points is contained inside the quadrilateral. So this is an example of a non-convex quadrilateral. A convex quadrilateral, if we draw a line segment between any 2 points, it's going to be on the interior. Okay, so that's the idea of convex versus non-convex. And again, you can prove that, but that's going to be helpful to talk about one last result from hyperbolic geometry. Okay? Because I want to consider what happens if we have two triangles have 3 pairs of angles congruent. Okay. Now we know that in Euclidean geometry, we have angle, angle, angle essentially. We know that this means that the triangles are similar, but not congruent. Okay. Not necessarily congruent. They could be congruent, but they don't have to be. But they do have to be similar. So in hyperbolic geometry, what would this lead to? So one case of this would be, we have 2 triangles with all 3 angles congruent. So we're going to suppose that we have 2 triangles, 3 pairs of angles congruent. Suppose the triangles are not congruent. So that would mean that, of course, that the side lengths are the same, right? So we would have one of 2 possible arrangements here. We could either do a transformation so that we have something that looks like this. A, B, C, D, E. So, here we have like so. So I could either kind of put them together so that we have this situation, or transform them so that one of the angles that's congruent corresponds in the 2 triangles. So this is kind of case 1. So what would happen in this case? Well, in this case, notice that this angle CBD and this angle BCE, they're going to be supplementary to the ones above them, right? Okay. So in this case, the measure of angle CBD plus the measure of angle ABC is going to equal 180. Well, if that's the case, ABC is congruent to ADE, so that tells us the measure of angle CBD plus the measure of angle, let's say it correctly, plus the measure of angle BDE, starting to lose track of points, would also equal 180 degrees. And then furthermore, the measure of angle BCE plus the measure of angle ACB would equal 180 degrees. They're supplementary. Well, if that's the case, ACB is congruent to CED. So BCE plus the measure of angle CED equals 180. Well, that's a problem because now we have angle pairs here that add up to 180 and here that add up to 180. So the angle sum of this quadrilateral, BCED is 360 or 2 pi, which is a contradiction. Interesting. So this is not a possibility. Okay? The second case, and this is going to look odd for Euclidean geometry, but perhaps it's a possibility. We want to consider the possibility for hyperbolic geometry, is that we have something like this. So we have E and we have D, and then again we have congruent angles 1, 2, 3. Right. So let's suppose we have two triangles. So watch carefully here. My two triangles are ABC, which is in blue, and ADE, which I'm outlining in red here. So we have those two triangles that have angle sums congruent. Well, in this case, we also have a problem because I need to name this, let's name this point right here F. Okay. Well, if I look at triangle, I could look at a couple different ones, but let's look at FCE. Okay. We notice that angle BCA is an exterior angle of triangle FCE, but it's congruent to opposite interior angle FCE or FEC. In other words, so we have two angles right here that are congruent. One of us is an exterior angle, and that violates the exterior angle theorem. Contradiction of the exterior angle theorem. So what does all this lead us to? This tells me that in hyperbolic geometry, we have a theorem that two triangles are congruent if the three pairs of corresponding angles are congruent. Okay. In other words, angle, angle, angle is a congruence criteria in hyperbolic geometry. We know it's not in Euclidean geometry, but it certainly is in hyperbolic geometry. So that's a nice result from hyperbolic geometry. Again, is a little bit non-intuitive, right? It's not what we would necessarily expect based on our experience with Euclidean geometry. So now I want to switch gears entirely, and I want to talk about a different type of geometry, because we've made a couple assumptions here. In Euclidean geometry, we say, if we have a line L and a point P, in Euclidean geometry, we assume that there's exactly one line through P parallel to L, right? In hyperbolic geometry, we assume that there is more than one line through P parallel to L. Okay. So the next case should seem obvious, right? Like the last case here is that there are no lines through P. This is the only case we haven't explored parallel to L. And in fact, we call this elliptic geometry. So elliptic geometry is what I want to explore a little bit today. Now, again, elliptic geometry has this characteristic that there are no lines through a point parallel to a given line. Okay, so this is just like we talked about the characteristic of hyperbolic geometry. This is the characteristic of elliptic geometry. Okay. Now this has some fascinating consequences, but before we get into those real quick, let me share a model for this. One really helpful model is to think about a sphere. Okay. So a globe. And the lines, so the points are points on a sphere, and the lines are great circles of the sphere. So the lines here are, anything that could be an equator. Okay, hopefully you get the idea there. It's not a beautiful picture, but hopefully it'll work. So if you think about the great circles as the lines, you can start to see some of the things that are going to happen here. Okay. So what we have, so if we have, say we have a line in elliptic geometry. Okay. Let's say we have some line C, well, your book calls it CG. We'll use that as well. Okay. If we have two lines perpendicular to it, so let's say that we have these 2 points up here, H and I, okay, so that, and we can drop perpendiculars from both of them, E and F. Okay. All right, so if we have lines HE and lines IF are both perpendicular to line CG. Well, I know that these two lines cannot be, I know that they can't be parallel, so they have to meet somewhere, right? So they have to meet eventually. We'll call this point A. Okay. And in fact, if you think about this on the sphere, just think about an equator here. If you're on the sphere and you have an equator and you have two lines perpendicular to it, well, they kind of have to meet here. And where would they meet? They would meet, if this is an equator, they would meet at a pole above and below. So in fact, this is exactly what would happen here. They would have to meet here as well. Okay. And so it turns out that any line from A to here would actually have to be perpendicular to CG, and it would meet down here. So there's actually a whole bunch of lines that do this. Okay. So just like on a sphere, every line from this pole is perpendicular here and meets at the other pole to this equator. And so every line like CG has these two poles such that every line from the pole is perpendicular to the segment. Okay, so we say A and B are poles of CG, and we say CG is polar to A and B. Okay. So this idea of having a pole relative to every line is really quite helpful, and allows us to prove some stuff about elliptic geometry that is kind of, I about said parallel, is analogous, let's say, to what we proved in hyperbolic geometry. So, for example, we can still have a Sacchari quadrilateral in elliptic geometry. So we can have a Sacchari quadrilateral where we have this and this and this and this, right? A, B, C, D. And I know in a Sacchari quadrilateral that if I join the midpoints of the top and bottom, that this is going to be perpendicular to both. That is that's the same proof we did in hyperbolic geometry because it uses no assumptions about parallel lines. Okay, so we know that the midpoint is, the line joining the midpoints is perpendicular to both the summit and the base. Okay. So what we'll do here is if we have EF, this midpoint right here, we can say, let's let O and O prime be the poles of that midpoint segment, EF. Okay. So essentially we're going to extend these out like so, and we know there have to be poles, O and O prime. Now keep in mind, we know from previous that in neutral geometry, hyperbolic, elliptic, or Euclidean geometry, that the summit angles are congruent, right? We proved that, and it requires nothing, no assumptions about parallelism. So we want to know, and we know that in hyperbolic geometry they are acute. So what about in elliptic geometry? Well, if you just think about this on a sphere, right? Basically what I'm doing here is I need to construct perpendiculars, and then I'm looking at another line here. Well, it kind of looks like these should be obtuse, right? So why would that be? Well, we've already found the O prime here is the pole for FE. So now I want to think about the pole for BC. So BC, if we go along this right here, it should have a pole, we'll call it X. Okay. So we'll let X be the pole on BO prime of BC, right? So that tells me that angle XCB must be right. So angle BCO prime must be acute. Okay. And if BCO prime is acute, then angle BCD is obtuse. Okay? Which implies then also that angle ADC is obtuse. So in elliptic geometry, we have that the summit angles of the secary quadrilateral are congruent, which we already proved for any of these cases, and they are obtuse. Well, there's a short jump then. If we take a Lambert quadrilateral, remember where you have three angles? We just reflect it over this side with two right angles, and we have a secary quadrilateral. And so this tells me that it's a very short jump. I'm not even going to write the proof out formally. I'm just going to introduce the argument here that, look at the picture, the fourth angle of a Lambert quadrilateral is obtuse. Then we can make a very short jump to right triangles. So we take a right triangle right here, and we make this construction we did before where we look at the midpoint of the hypotenuse, and we construct a perpendicular right here, and then we do this so that, I guess I should give some labels here, A, B, C, we'll call this D, and then E, and then F. And we construct this in such a way that FAD is congruent to DBE. Use a different color here so it stands out a little bit better. And we also do this in such a way so that AF is congruent to BE right here. So just like before, this gives us that triangle AFD is congruent to triangle BED. So we get that these angles are congruent, and so FDE collinear. Okay. And angle AFD is right, because I should have drawn this a little bit bigger. This is right. This must be right as well. Okay. So angle AFAC is obtuse because it is the fourth angle of a Lambert quadrilateral. Okay. Well, if that's obtuse, then the measure of angle FAD plus the measure of angle BAC is greater than 90. So we know that FAD is the same as ABC. So the measure of angle ABC plus the measure of angle BAC, there we go, is greater than 90. So the angle sum of the triangle ABC is greater than 180, or pi. Okay? So in other words, we have just justified the theorem that the angle sum of a right triangle is greater than 180 degrees or pi. And from there, it is a very short jump to the theorem, I wish I had just a little bit more room here, that the angle sum of any triangle is greater than 180 degrees or pi. Okay. So it was relegated to a corner of my workspace here, but it's an important triangle. Or it's an important triangle, an important theorem. And you can kind of see the relationship here, right? Euclidean geometry, we assume exactly one line parallel through a given point to a given line, and we get the angle sum is exactly equal to 180. In hyperbolic geometry, we assume that there's more than one line parallel to a given line through a given point, and we get that the angle sum is less than 180. And in elliptic geometry, we assume that there are no parallel lines through a given point to a given line, and we get that the angle sum of any triangle is greater than 180. And this should not be particularly surprising because you can have these poles in Euclidean geometry, elliptic geometry. So these right here, we already have 180 from, and then we have whatever this is right up here, okay, in this triangle. By the way, I forgot to mention earlier, because we have these two poles, you can have in elliptic geometry, these are going to meet down here. You can have a bigon or a biangle, bigon or biangle, which consists of just two line segments, which is very different from anything we've seen in hyperbolic or elliptic geometry. Okay, I've said enough about elliptic geometry, but hopefully you get a feeling for how this other assumption, this other characteristic about parallel lines affects things, because we get a slightly different world when we make slightly different assumptions than the axioms.